In this video, I wanted to discuss the various different ways of determining the area of a triangle, mainly covering three different formulas. Starting with the most basic, which most people, if you ask them how to find the area of a triangle, they'll have this formula memorized, and the formula goes area is equal to 1/2 base times height. Um, and I wanted to review for each of these formulas why they're true and look at an example of solving them, especially with regards to trigonometry as we've been studying. So with this formula, there's actually a quite simple reason why this is true. If you think about a triangle, like let's look at a generic triangle as the ones we've been looking at, not necessarily right, but it would apply to a right triangle as well, with angles A, B, and C. If you think about a triangle, you can always think about a triangle as being boxed in by a particular rectangle. So this would be side B, side C, and side A. But if we were to build a rectangle, around this triangle, notice that the rectangle forms each triangle within the rectangle. If we extend the top of the triangle down to the bottom, which is that quantity we use with the law of sines and law of cosines, basically we can break a non-right triangle into a right triangle, into two right triangles, and that helps us solve more properties about them because with right triangles are a lot simpler in a lot of ways, like with the Pythagorean theorem and with SOHCAHTOA. But anyways, notice that if I break down this triangle inside of a rectangle into two separate right triangles, each one of these forms another rectangle. And if I'm focusing on each rectangle individually, each rectangle is formed around a right triangle. And a property about a right triangle, which you probably remember, is that it's exactly half of the rectangle which it's inscribed within. But basically, if I was thinking about the area within this space, it's cut exactly halfway. It's not like right down the middle, but even if it's cut along the diagonal, it still cuts that segment of area directly in half. And since that segment of area forms a rectangle, we know that the rectangle is length times width. So what we get is the area within the triangle is half of the area of that rectangle. And on the right-hand side as well, we get another rectangle where the segment of area within there is also half of a rectangle, which would have half the length times the width of that particular rectangle. But if we add up each of those, it would be half of length times the width of the first, plus half of the length of the width times the second. That would just give us a sum length of, well, 1/2 base times height, because the base is the measurement of the bottom of the triangle, which you could call the base any of the sides, but in this case, it just makes sense to put it as that one. And the height would just be, well, how tall is it? What's the width of this particular rectangle? And notice that the entire rectangle would obviously have an area of base times height, length times width, as a general property of multiplication. And since our triangle forms exactly half of that in two components, it makes sense that the area of a triangle is 1/2 base times height. And the reason I bring this formula up is because in trigonometry we have a few other alternative versions of the formula which actually stem from the same generic formula 1/2 base times height, which is just true by basic geometry. But basically, if we look at the next formula, this is the area of a triangle with sides of length A and B with included angle theta is area is equal to 1/2 AB sine of theta. So let's say in this particular triangle, let me redraw it so we can see it a little bit better. Let's try to examine why this, what I sometimes might call the included angle formula, is true. And so basically, also one thing that's important about this formula is that the angle theta that you use within the formula must be the angle in between the two sides of the triangle. That's what included angle means. So if I was talking about these two sides, I would need to make sure to know the angle in between them. I couldn't use this angle over here. That would not work in the formula. But if we look at this and we want to know, well, why that's true, again, if we kind of focus on that height component, if we were to know the height, we know that the area of this triangle is equal to 1/2 base times height. But basically, we could figure out the height using the sine of theta, which is kind of what this formula is implying. And if I look at this triangle, well, again, assuming I know the given theta, this forms a right triangle, and the sine of theta must be equal to, by SOHCAHTOA, opposite over hypotenuse. And while usually we use h for hypotenuse here, h is height, so unfortunately it's a little bit, not perfect letter choice, and a usually means adjacent, not hypotenuse, but I think you catch my drift in that sine is always opposite from the angle divided by the hypotenuse, which a is the hypotenuse of this particular green triangle. But anyways, what that leaves us with is the height is equal to a times the sine of theta. And if I substitute that into the formula down here, that would leave us with a is equal to 1/2 base times a sine theta. Or, as the formula indicates, the area is equal to 1/2 b times a, or a times b times the sine of theta, assuming the angle is in between them. And this applies to any triangle, doesn't just have to be a right triangle. And also, more importantly, the reason why we care about this formula is, well, this formula is nice if we know the height. But in some situations like here, we don't necessarily know the height, and the 1/2 base times height formula might not be directly applicable. Now, you could figure it out in the same way that we figured out this formula, but it's just an alternative formula that you could memorize in order to find the area without having to think about it. Not that thinking is bad, but it's nice to know, the general outcome. But a common mistake with this question, like say we were trying to find the area of this triangle from the packet, would be to just take 1/2 10 times 3, and that's that. But basically, since the height, this value is not the height of the triangle. That's kind of the important thing about the most generic version of the formula. H must be perpendicular to the base. But notice that this angle is 120. It's not perpendicular, so this cannot be used as the height. But we could imagine, well, the height would actually look more like this. Oops, did not mean to do it that way. The height would be how tall is the triangle. So it would be, perpendicular to the base. And that's something that we're not given. So we could figure this out by we have a triangle here and we have all the information to actually solve this triangle. But it's a little bit simpler to just use the included angle formula, which instead of having to do anything else, I know two sides of the triangle A and B, and I know the angle in between them is 120. So the area must be equal to 1/2 base times height, which in this case would be 3 times the sine of the theta. And that basically 3 sine 120 would give you that height value based on SOHCAHTOA. Or in this case, it's going to be 15 times the sine of 120 degrees. Sine of 120, we could actually do that without a calculator, right? Because 120 on the unit circle is going to be past 90 over there. And the sine value would be the tallest one, √3/2. So this would be 15 times the square root of 3/2, which would be approximately, I think I've still have forgotten to fix my calculator. Yes. So we're going to use Google once again. 15 times the square root of 3 divided by 2, which is approximately 13 units. And so since this is area, just as a reminder, that would be in square units because it's calculating the size of the triangle, the amount of space within it, not any particular length. Which is a just another formula we could use in particular situations. So if another point here is, once you've solved a triangle, once you know all its sides and angles, we could always use this formula, and we kind of have, after talking about the law of sines and cosines, we pretty much know how to solve any triangle if it's possible. If it's possible, we can use those laws. If it's not possible, we just can't solve it, so why bother? And basically, we could also then find its area, basically find all the properties of this triangle in succession. And this is just a helpful formula to remember in that case. And actually, at the end of the packet, sorry, I'm a little bit out of order here in the way I'm going through the lecture. But there's also another formula which comes on page 7 of your packet, which is what a lot of people call Heron's formula. And it's another separate different way of solving a triangle. Actually, I'd rather not go through the derivation because this video is already longer than it needs to be. But the derivation looks something like this. It's derived from those same formulas that I was talking about. And a little bit more geometry and algebra and trig later, we wind up with this particular formula. So instead of diving too deeply into that, that's something where you could look it up on YouTube, find out why if you really want to look into that further. But I think we've it's just another formula with a different specific purpose, which is kind of what I want to focus on. But anyways, this is the area of triangle ABC is given by the square root of s times s minus a times s minus b times s minus c. Where S is kind of something new, it's like, what is this S? It says it's called the semi-perimeter of the triangle, aka half of the perimeter. So this is not really a super imperative term, but it's just used to make Heron's formula a little bit cleaner and make it look as simple as possible. But basically, what is the perimeter of the triangle? Cut it in half. There's your semi-perimeter. So let's say we were to look at the same triangle we just did. Let's examine it looking at Heron's formula instead, just as as an exercise, and we'll make sure it gets the same answer, because at the end of the day, all of these formulas do the same thing. They figure out the area. They should yield the same results. And anyways, that's good to know. But like looking back at this triangle, let me get back in there. In order to use Heron's formula, we need to know the perimeter. We need to know all three sides, A, B, and C first. So that's kind of an alternative way of like, when would I want to use Heron's formula? This problem, it's obviously easier to just use the included angle formula because I have everything I need to know. But in a case where we don't know an angle, if we were to just know the three sides, Heron's formula is perfect because it just uses the sides and the perimeter. It doesn't need to know any angles. So it's kind of like the law of cosines version in area terms, because if we have a side-side-side triangle, we can just get the area directly. Also, before we do this example, why should we care? Why do we need all these different formulas? Well, in certain contexts, it's a lot easier to use Heron's formula because there's no trigonometric function required. Whereas the included angle formula, notice it has a sign in it. Computationally, that can be more difficult, and there's reasons why we might want to use a square root formula instead, mathematically speaking. And depending on the context, one might be simpler and easier to calculate. So for those of you in the computer science brand of study, sometimes certain formulas work nicely in computer programs, some don't. But it's always nice to know alternative versions. And this is not the end of formulas for area. There's others out there too, which contextually may be simpler as well. But anyways, Heron's formula is fairly easy to remember in my opinion. The area is equal to the square root of s times s minus a. It's basically you just take the semi-perimeter and multiply by the difference of the semi-perimeter with each side. And take the square root of all that, and that seemingly magically will find the area of a triangle. But again, it's not really magic. It just involves quite a bit of algebra and geometry and stuff. But anyways, to do this, we're going to need to know the third side of the triangle. But actually, since we know this side, the height, which is 3 times the sine of 120, just 3 root 3 over 2, we could actually use the Pythagorean theorem to solve that length. And actually, I lied. We can't use the Pythagorean theorem because we have not found this. Actually, we could find the length of this part of the triangle, but it's probably easier just to use the law of cosines to find the third side in this case, because I have a side angle side triangle. I could always solve this via law of cosines. So if we went ahead and used the law of cosines, we'd have that b squared is equal to a squared plus c squared minus 2ac cosine angle b. And I know everything in this equation except for little b, which is, of course, this side up here. And that side would unlock the perimeter and all three sides, which is what we need for Heron's formula, is S, and obviously ABC. But basically, I could also take the square root of each side, which would leave me with b. B is equal to the square root of a squared plus c squared minus 2ac cosine b. What I could do is just type all that in, because I know a is 3, c is 10, and angle b is 120. So let's go ahead and do that. That would leave us with the square root of 3 squared plus 10 squared minus 2 times 3 times 10 times the cosine of 120 degrees. And assuming, I think I got everything in there. I'll double check my numbers here in a second, but assuming I got all those numbers, I remember all those right, that would leave us with side B being approximately 11.8. Let me just go back to make sure I got those numbers right. 3 squared plus 10 squared minus 2 times 3 times 10 times cosine 120. Yes. So B is approximately 11.8 from the law of cosines. And once I know B, I now can use Heron's formula. And the whole point is I just wanted to do some examples of finding the area of a triangle. So using this formula, we figured out the area is approximately 13 units by included angle formula. We should obviously get the same result from Heron's formula. And so once we know that, let me go ahead and erase this just because I'm running low on space here. There is equal to the semi-perimeter times s minus a, s minus b, and s minus c. And I know a, or this is c, this is a, this is b. So I know all these guys. And then s is just the sum of all of them divided by 2, because the perimeter is, well, 11.8 plus 10 plus 3. And then I cut that in half to get the semi-perimeter. So the semi-perimeter here would be approximately 11.8 plus 10 plus 3. And then I need to divide all of that by 2, which would give me 12.4 for the semi-perimeter, approximately, of course. I'm all doing estimation here because 11.8 was an estimation from the law of cosines, not exactly 11.8. So the area should be equal to the square root of 12.8 times, well, s minus a would be 12.4 minus 3, so that's 9.4. S minus b would be 12.4 minus 11.8, which would be 0.6. And s minus c would be equal to 12.4 minus 10, which is 2.4. And so if I take the square root of all of that stuff, that should give me the area. And it should be consistent with the other formula. That's kind of what the point I'm trying to get across here. But if we do all that, hopefully we're going to get 13. And it's a little bit more than 13, but this, as something I've reminded you about before, be careful when you're rounding in each of these problems, because if I round things up or round things down, every time I round, there's going to be a little bit of error. And if I use that calculation again, there could be compounding of the error, meaning it could get worse and worse and worse. In this case, it's off by, well, the other formula was a lot more exact, because here I did not use any rounding, but here I rounded the 11.8 to get the semi-perimeter, which was also rounded. Then in every single one of these, they were all rounded. And actually notice that they were all rounded up a little bit. So since each one of these was a little bit rounded up, those all compounded, and they ended up giving me an answer that was a little bit too high. So word of warning is just, well, don't do what I did, really, if you want to be exact. But just, I would use maybe 5 or 6 digits instead of 3 significant figures, or 2 even in some cases, like I did right here. And that will obviously save you, give you a more accurate answer. At the end of the day, I'm not too concerned with accuracy, but you can tell how, if we were building a building or wanting to know exactly the properties, a rounding error of, that's off by a tenth or almost 2/10 could be pretty significant and could lead to some issues with the shape itself. But anyways, what to take away from this is area can be solved in numerous different ways, and it's just nice to be aware of all of the different formulas. See ya in the next video.